Welcome everybody to the department seminar. Our speaker today is Dr. Micah Ziegler from MIT's Institute for Data Systems and Society. He did his PhD in chemistry right in the Bay Area at UC Berkeley. He's also worked in Asia for a while, and now he's at MIT. So Micah, all yours.
Thank you. Thank you all for logging in and attending, and good afternoon. As just mentioned, my name is Micah Ziegler. I am a postdoctoral associate at the Institute for Data Systems and Society at MIT. And today I want to talk a little bit about how we can help enable rapid technological change. And I'm going to be describing technologies that we hope will help us mitigate climate change. And I'll be relying on quantitative insights from 3 decades of improvement of lithium-ion battery technologies. So over the course of this talk, I want to go through 4 general ideas. First, I want to give you a kind of brief introduction to why we study technological change, give you a sense of our goals and our motivation. Then I want to provide some of the background ideas and research that informed the direction of most of the research I'll be talking about today. And that came from understanding what we might need from energy storage technologies in the context in which they might operate. Then I want to go into detail on investigating how we can enable the technological improvement of energy storage technologies. And then finally, I would like to leave you with a few conclusions and maybe some implications for those who are conducting research or designing policies or deciding where financial investments might go. So to start, why do we study technological change? Well, at least I study technological change because I consider it one component of a broader data-informed pragmatic approach to achieving at least some environmental goals. The entire approach is outlined here, and we'll go through it step by step quickly. But before that, the premise of this approach is essentially that we have limited time and limited resources to reach our environmental goals. And so I want to see if we can be more intelligent in how we spend that time and spend those resources to, for example, avoid the worst possible impacts of climate change. This is a general approach that describes one way in which research can have an impact on our environmental goals. And the research I do comprises the first 3 steps. So starting with the first step, we need to understand what we want from technologies and the context in which they might operate. Here we're trying to determine how technologies will need to perform to achieve our energy, environmental, social, economic goals, and how what we require of these technologies might change over time and space. For example, we already can approximate or project that different communities and countries might need different portfolios of technologies to reach their energy and social goals. In this type of research, we can use models and simulations to study technologies and the systems in which they operate. And we can use our results to identify challenges and opportunities and to, for example, set performance targets. Given that understanding, we can then identify promising features of technologies that can help us meet these targets. I should mention here, when I talk about technologies, I'm using a broad definition. Technologies can refer to pieces of hardware, like a photovoltaic module or a lithium-ion battery cell. They can also refer to entire systems, like the transmission system for electricity in the US could be considered a technology. Technologies also don't need to be tangible with this definition. For example, an algorithm that allows an energy storage system to be operated more efficiently, that could be considered a technology. Even instructions for how to bury transmission lines in a more inexpensive fashion, that could also be considered a technology. And when I'm talking about identifying technologies, I'm actually saying we're going to identify features of technologies. And that's because sometimes it's not necessarily prudent to try to pick and choose technologies. In some cases, there's a lot of uncertainty as to how technologies might improve or how they might change over time. And so sometimes it's better to try to identify a feature of technology. So instead of saying explicitly photovoltaic modules or wind turbines, sometimes you might want to identify, well, something that produces electricity while having low to no greenhouse gas emissions. So given that understanding and the identification of some technology features, then we can investigate and develop strategies to improve and deploy these technologies. So for example, if let's say we know we need to bring the cost of a technology down, what can we do to help us bring that cost down most effectively, given our limited time and resources? Do we just need more research and development? If so, which avenues of research might be most effective? Or do we just need to scale up manufacturing? Do we need to build bigger manufacturing plants and benefit from economies of scale? In this type of research, we try to determine what we can do, how we can use the tools we have to help the technologies reach the targets we set. Next, people need to implement these strategies. This means folks who are developing new technologies, doing the research and development, or folks who are crafting public policies or deciding where large financial investments should go. They're making a series of decisions, and we're hoping that the research that I described in the past 3 steps can inform those decisions so that they can enable the more rapid improvement of technologies. Finally, technologies change and our objectives might change. And ideally, the world changes for the better. And then we come back to the beginning of the cycle, because considering we have different technologies and maybe new objectives and a different world in which they operate, we want to make sure we're still on the right track, that we want to reevaluate and ensure that we really understand what we need from these technologies. So as I mentioned earlier, the research I do comprises the first 3 steps of this pragmatic approach. And most of what I'm going to be discussing today is this 3rd step, because I firmly believe that understanding how and why technologies change can inform strategies to enable or even accelerate their improvement. But before we get into that, I want to give you a sense of some of the background that kind of the context for this research, which came from understanding what we might need from storage technologies. And so I'll briefly summarize some elements from the first 2 steps in this pragmatic approach. And the major question is, if we're going to study how to improve energy storage technologies, which features of energy storage technology should we focus on? Energy storage technologies can have many different technology features. Energy efficiency is one of them, their cost, their ability to respond rapidly to different, let's say, supply changes or demand changes for the energy. And to get a sense as to what features we want to focus on, we can look at how energy storage technologies might be used. For example, one popular choice would be in electric vehicles. And we start looking at how electric vehicles are trying to compete with existing cars, for example, and we see that people want to bring the cost down. And a major cost of an electric vehicle is typically the battery, which is the energy storage system. And people have set cost targets for electric vehicles. And typically, because the battery is such a large component of the cost, they look at targets where they take the cost of the battery and they scale it by its energy capacity. You get these targets with units of dollars per kilowatt hour. And so this is a feature of energy storage technologies. It's energy capacity cost. And it's important for electric vehicles. It's not necessarily the only important technology feature, but it's an important technology feature. And we actually find that the same feature, energy capacity cost, is important for helping integrate renewable energy resources into a broader grid in a cost-effective fashion. So let's say you have solar panels and wind turbines and a battery, and you want to provide some consistent output profile that looks something like a coal-fired power plant in terms of consistent baseload energy. The overall cost of that process, of the energy you produce, is really sensitive to the energy capacity cost, the dollars per kilowatt hour of the battery. And so this was actually a major result of some work that I and a few others published a couple years ago. And it's something that we've seen over and over again with different studies that use different methods and data sets. So we're pretty confident that energy capacity cost is important both for electric vehicles and for integrating renewables into a broader grid. Then, given this technology feature, we want to next pick a technology to study. Now, I'm not saying we're going to pick this technology and promote its adoption or necessarily pick a technology and say, this is what policymakers should invest in. We're just trying to figure out how energy capacity cost of a storage technology can change over time. We have many different storage technologies you can look at, everything from pumped hydroelectric, where you pump water uphill when you have extra energy, and then let it flow back downhill through a turbine when you need that energy back. We can compress air underground. You can store energy in batteries, which would be electrochemical storage. You can store energy in the bonds and molecules. That would be chemical storage. We have flywheels, thermal storage. A popular option that's received some media attention recently is stacking concrete bricks. For some of the reasons I mentioned earlier, we decided to focus on electrochemical storage batteries, specifically because they're relevant to electrification of our transportation system, and they're increasingly being deployed in stationary energy storage applications. So given the sense that we want to focus on the energy capacity cost of storage, and we're going to look at how it's changed for batteries, then we can begin to investigate how to enable technological improvement. So we've moved on to that third step in our pragmatic data-informed approach. And we're going to narrow a little bit more, and we're going to say that we're going to study lithium-ion batteries. Why? Well, at least when we started this research, we had this general impression that they might be improving rapidly. I'm showing a visual progression of that improvement on this slide. In the upper left, I'm showing a photo of an electrochemical cell from the early 1980s, which could be one of the earliest cells to use the shuttling of lithium ions back and forth to store energy. In the center top of the slide, I'm showing a photo of the first commercially available lithium ion cells produced by Sony in the early 1990s. And then in the upper right, we have an aerial photo of a stationary energy storage facility in 2018 that's being used to support an electric grid, but still relying on the shuttling of lithium ions back and forth to store energy. So visually, at least, lithium ion technologies appear to be improving quickly, but how quickly? If in fact they haven't improved that quickly, then maybe it's not a good model to study. But if they have improved quickly, then we can try to figure out what led to the improvement we observed. What lessons can we learn from that? Why did they improve? And based on that information, how can we enable further improvement for energy storage technologies? What should researchers and policymakers and businesses do? So to answer these questions, I kind of take the same general approach, which is I take a more comprehensive look at all of the data I could get my hands on. I rigorously analyze these data, and then I try to distill robust insights that can improve decision-making. So to the first question, how quickly did lithium-ion batteries improve? Well, I wasn't the first person to look at how the cost of lithium-ion batteries changed over time. And in fact, I'll mention here that we're going to use the price at the cell level as a proxy for cost. Actual manufacturing cost data are few and far between. So many people use the price of lithium-ion cells as a proxy for that. And people have looked at how that price, again, scaled by the energy capacity, has changed over time. And I'm plotting the different data series that researchers have used here. And you can see that there's a pretty wide sense of the uncertainty. There are different estimates. And you might notice that I've plotted this on a logarithmic scale on the y-axis. So small differences in this plot actually are really large differences in people's estimates of how much a lithium-ion battery costs in a given year. And not just the absolute values, but the rates differ considerably. So for each one of these series, you can estimate the annual decrease ratio or the annual amount by which the price changed. And for these series that researchers had used, it changed at this rate ranged anywhere from 9% up to 29%. And that's a really big difference. If you just took these data and projected forward in time, you would get these decade-long windows for when lithium-ion technologies might cross a threshold, a certain cost or price target, for example. And that's just coming from the uncertainty in the different data series that folks were using to try to figure out how quickly this technology improved. So our first step to trying to figure out how quickly did lithium-ion batteries improve was to develop improved estimates of price decline. I'm showing the results of that analysis here. We found that lithium-ion technologies, the price of them decreased by 97% between 1991 and 2018. We figured this out by getting all the data series we could, so all the data series those previous researchers had used, as well as other data series that did not appear to have been used before. We harmonized the data series and point estimates. We went back to original sources to make sure we weren't double counting data series and we could get better metadata. And we then categorize the data. So lithium ion cells come in different shapes. There are cylindrical cells, prismatic cells, and pouch cells. And the price of a cell is often correlated with the shape. Cylindrical cells tend to be less expensive. And so we categorize the data. On the plot here in blue, I've shown all of the data that refer specifically to cylindrical cells, while in orange, I'm showing the data that refer to all types of lithium ion cells or were otherwise not specific. And within those two categories, we could develop representative series using the best available data we had for any given year. And I've plotted those representative series as these bold dashed lines. And there's a considerable difference in the trajectory of price decline for cylindrical cells and all types of cells. And these types of data series can be used in top-down studies of cost change. So what do I mean by a top-down study? Well, I'll briefly kind of give you an overview of two sets of methods that we use to examine how technologies change over time. There are phenomenological models. These are the top-down methods. They require some high-level data on technological progress, such as a falling cost of a technology and then potential drivers of that progress. And then there are these bottom-up mechanistic models. They require a cost equation and considerable data on the design, the engineering, the input prices, the manufacturing of a technology. And these allow you to kind of estimate how different changes in a technology contributed to, for example, cost change or some other measure of technological progress over time. We're going to use both sets of these methods when just investigating cost change for lithium ion technologies over the course of this talk. But we'll start with the phenomenological models because you can use these to estimate rates of improvement. So they tend to have the kind of equation there. They have the form that I'm showing here, where on the left, you typically have the log of a measure of technological progress, such as the scaled real cost of a technology. Real simply means we're correcting for inflation, and scaled is just like what I described earlier. We're taking, for example, the cost of a cell and scaling up by the energy capacity. On the right-hand side, you have some sort of driver. So you can look at, for example, improvement of a technology versus time. And colloquially, we refer to this as Moore's law. You can look at improvement versus cumulative production. And colloquially, we often refer to this as Wright's law. You can look at it versus annual production, which we will call Goddard's law. And then you can also look at cumulative R&D activity, which is sometimes approximated by the number of patents filed. So as I mentioned, you can use these models to estimate rates of improvement. One improvement rate you might have heard of is the learning rate, which is what you estimate when you apply Wright's law. And it's essentially an estimate of the cost decline observed upon a doubling of cumulative production. So to estimate these rates, you need your measure of technological progress, which we already have, the price per kilowatt hour series for lithium ion technologies. And you need an estimate of how the driver changed over time. So we went out and collected as much data as we could. For example, we're going to use measures of market growth as a proxy for production. We similarly harmonized and categorized the data. So I have representative series here for all types of cells in orange and cylindrical cells in blue. We found that market size increased by 4 orders of magnitude over about 27 years. And we also went ahead and got data on patents, and we got other types of possible driver data. And given all of this, we can then fit those models of technological change. And I'm showing the results of fitting some of those models here. On the left, I'm showing Moore's law, where we look at price decline versus time. In the center, I'm showing Wright's law, where we're looking at price decline versus cumulative production. And on the right, I'm showing the analysis of price decline versus the cumulative number of patents that were filed. And for Moore's law and Wright's law on the left and in the center, we were able to split our analysis into one that's specific to cylindrical cells and one that covers all types of cells in blue and orange, respectively. And for example, when you look at price decline versus time, you can estimate that annual decrease ratio. And we see that cylindrical cells and all types of cells fell at about the same price versus time, about 13% a year. But if you look, for example, at the learning rate, how quickly the price fell with cumulative production increases, we find that cylindrical cells had a learning rate of 24%, whereas all types of cells had a learning rate of 20%, which is a considerable difference because these learning rates come from the exponent of a power law. So while it might seem like it's only a 4% difference, because it's in an exponent of a power law, it really is a pretty big difference in a measure of how quickly a technology improved. But I went ahead and I did this analysis and I got these results, and it felt a little lacking. And it's because we were just looking at how the price per kilowatt hour changed over time. Lithium ion technologies didn't take off in the 90s because they were the least expensive energy storage technology available. There were less expensive batteries, lead acid batteries, nickel metal hydride batteries, they were all less expensive. What enabled lithium ion technologies to take off was that it allowed you to hold a camcorder in the palm of your hand, and then later a cell phone and a laptop. It was the ability to hold a lot of energy in a constrained volume that really led to lithium ion technologies taking over a lot of mobile applications, and then power tools, and then eventually things like electric vehicles and e-bikes. But we weren't really examining that improvement. I felt as though we were only getting measuring a portion of the improvement. So I returned to that original formulation of the phenomenological model, and then took a closer look at the left-hand side of this equation. What is the measure of technological progress? And what are we doing when we say it's the price per kilowatt hour? Well, we're kind of saying it's the cost for a given service. And we're saying that the cost or price of a cell is going to be scaled by the service. And if we're going to say the service is just the energy capacity provided per cell. But like I said, I kind of got the sense that lithium ion technologies provided more than just energy capacity, they provided energy density. So I wanted to see if we could consider other cell level attributes. And we went ahead and applied a multiplicative model. We're using this as a model that's as simple as possible or as parsimonious as possible while still capturing the effects that we're interested in. So we're going to say that the service per cell is equal to the product of different cell level attributes weighted by these exponents. And so if you wanted to incorporate another cell level metric, you could estimate the service provided per cell as the product of, for example, the energy capacity and the energy density. You can then take the price of that cell and divide it by this new expanded definition of service and rearrange a bit. And we get to the bottom of this slide where you have a price per service can be estimated by the price per energy capacity, a data series that we have, and an estimate of how volume changed with energy capacity, which is just the inverse of energy density. Because we don't have additional data on how people valued these two metrics versus one another over the course of improvement of lithium ion technologies, we're just going to set the exponents equal to 1. And so we could actually estimate how price per service changed with this expanded definition of service if we had data on how energy density changed. So I went out and kind of reverted to my approach of let's collect as much data as possible. I collected data series on how energy density changed and many data points. All the data points you see here refer to commercially available lithium ion cells. In blue, we have cylindrical cells. In green, we have prismatic cells. And in purple, we have pouch cells. We combined all these data. We see that between the early 1990s and the early 2010s, there was almost a 3-fold increase in the energy density of lithium ion cells. We also see an increasing spread in the energy density of lithium ion cells. And this in part reflects the fact that not every application of lithium ion technologies over time needed the most energy dense cells available in a given year. Sometimes they could use something with an energy density that was available a few years ago. But we still wanted to develop representative series that gave us a sense as to how rapidly the technology improved. And so we decided to use the 98th percentile to develop representative series, which we did for cylindrical cells and all types of cells. Again, plotted here as these bolded dashed lines, which kind of follow the top of this envelope of data. So we have this data on how energy density changed over time. We already have the representative series on how price per energy capacity changed over time. We can then go back and examine those same phenomenological models and fit them to these data. So I'm showing the results of that analysis here. In orange on each one of the plots, I'm showing the results of the analysis when the service provided by a cell is just the energy capacity. So the analysis I showed a few slides ago for all types of cells. In purple, beneath each one of them, essentially the lower series, I'm showing the analysis when the service of the cell is expanded to include energy capacity and energy density. And we see in all three cases that we had faster improvement when we're considering more dimensions of that improvement. For example, the annual decrease ratio for all types of cells increases from 13% to 17%. The learning rate increases from 20% to just shy of 27%. So we see a dramatic increase in these improvement rates when we're considering not just how the price per cell went down, but also how the energy density per cell went up. So we have these estimates of how rapidly lithium-ion technologies improved, but we also need to kind of ask another question, which is compared to what? Are these actually a rapidly improving technology? Well, to do that, we need to compare them to other technologies. So we did just that. Here I'm showing the results of that analysis. On the left, I'm showing the annual decrease ratios for other estimates for lithium-ion cells in these floating histograms in gray and purple. And then I'm showing the annual decrease ratios, the improvement with it versus time, for a variety of other technologies in these colored histograms on the bottom of these two plots. So on the left, I have the improvement versus time rates, the annual decrease ratios. And on the right, I have the learning rates, the improvement versus cumulative production. And I'm showing the results of our analysis in these dotted lines that go from the top to the bottom of each one of these plots. And you can see, for example, when looking at improvement versus time, the annual decrease ratios, our estimates are actually lower than those provided for or estimated based on data that people had used for lithium-ion technologies in the past. You can see that our dotted lines are kind of to the left of the center of mass of the purple histogram that kind of floats in the middle of the plot. But already lithium-ion technologies look like they're improving more rapidly than many other technologies from the chemical, the energy, and other industries. And this is just when we say that the service for a cell is defined as its energy capacity. When we look at the learning rates, we see that our estimates for the learning rates are kind of between those people have estimated for lithium-ion technologies in the past. They're towards the top of energy technologies and kind of towards the middle bottom of chemical technologies. But then when we expand that definition of service to include energy capacity and energy density, our rates, of course, shift to the right. We estimate higher improvement rates. And we can see that lithium-ion technologies are improving considerably more rapidly than other technologies improved versus time. And now their learning rates are kind of towards the high end of energy technologies and towards the middle high end of chemical technologies. And so one potential implication of this work is that lithium-ion technologies might have this faster rate of improvement that could suggest that as essentially we use them for new applications. And if those new applications don't necessarily prioritize high energy density, we might see faster improvement along other dimensions. We're kind of saying that these rates that consider energy capacity and energy density give us a more holistic estimate of how quickly the technology improved. And so going forward for something like a stationary application where mass and volume restrictions are relaxed, we might see faster improvement. So we have a sense now that lithium-ion technologies have improved rapidly, including in comparison to other technologies, but we don't really know why they improved. To try to answer that question, we have to use the mechanistic models I mentioned earlier. This is a generally newer approach to studying technological change, so I'll give a little bit more detail. It's a dynamic bottom-up approach, dynamic in a sense that it takes into consideration how technologies changed over time, and bottom up because it relies on information as to how the technology is constructed. You start with a cost model. On the upper right of this slide, I'm showing the cost model that was published a few years ago for photovoltaic modules, where you take the cost of a technology and define it as the function of several variables. So here we're taking the cost of a photovoltaic module, where it's really the cost of the module scaled by the power that that module produces when sunlight hits it. And you can say that it's the function of, for example, the energy efficiency of the module, the price of silicon, the size of the manufacturing plant, and a few other variables. The amount of detail you put into one of these cost models reflects the importance of various features of a technology and your data availability. But then given one of these cost models, you can derive cost change equations, which allow you to estimate how the different variables influence the cost change between 2 points in time. Because we're looking at discrete time points, we have to use an approximation. But a major advantage of this approach is that it allows you to disentangle the impacts of multiple simultaneous changes to a technology when they influence the technology cost or performance in a non-additive fashion. So for example, when people have talked about why solar photovoltaics came down in price, some people have pointed to the falling price of silicon, whereas others have said, oh, well, people are just making them in much bigger manufacturing plants. Even others have said, well, really, it's the increase in energy efficiency of the modules. This type of analysis allows you to quantitatively estimate the contributions those changes had to overall cost decline between 2 points in time. Now, the other advantages of this approach are that because you start with a defined cost equation, you lower your chance of double counting. And you can also use this approach retrospectively and prospectively. And today I'll be describing a retrospective approach where we apply this methodology to lithium-ion technologies to try to understand why they came down in cost so rapidly, why they improved so rapidly. Here I'll just mention that the work I'm about to discuss is not quite published. It's accepted for publication and I've seen a galley proof, but it's not quite, we're not quite ready to have it shared publicly just yet. So if you want to discuss it publicly, if you could wait a couple weeks, we would appreciate it. And I also want to make sure we're all up to speed on what goes into a lithium-ion cell. As I mentioned, the top-down phenomenological models just require a sense of some high-level performance metrics and drivers, whereas this bottom-up approach requires a sense of what goes into a lithium-ion cell and how it's manufactured. I'm showing a simplified diagram of an electrochemical cell on the right-hand side of this slide. On the left-hand side of this diagram, we have the cathode. In a lithium-ion cell, the cathode is often a metal oxide, like lithium cobalt oxide is a prototypical example. Over time, people have found that you can replace the cobalt with a mixture of other first-row transition metals like nickel, manganese, and cobalt. So you see a wide variety of cathode materials that kind of have this metal oxide structure, but with different metals. On the right-hand side of the diagram, I'm showing the anode. In lithium-ion cells, this is typically made out of carbon, and very often it's graphite, which are basically sheets of carbon. And when you charge a lithium-ion cell, the lithium ions migrate from the cathode to the anode and actually sit between these sheets of carbon. Of course, the lithium ion doesn't just transfer over through a vacuum. It needs some help getting from the cathode to the anode. And that help comes in the form of the electrolyte, which is often a lithium salt like lithium hexafluorophosphate, dissolved in some organic solvent like a mixture of organic carbonates. And then when you discharge, the lithium ions go back from the anode to the cathode. The electrons can't travel across that way, so they have to go through current collectors, which are typically aluminum foil and copper foil. And then finally, you need to keep the cathode and anode separated, so that way you can store energy. And this separation comes in the form of a aptly named separator, which is typically a plastic like polyethylene or polypropylene, often with or sometimes with a coating on it. So given all of this information, as well as additional information as to what goes into a lithium-ion cell, we set up a cost equation for lithium-ion cells, or a cost model. I'm showing the full equation here with all 41 variables. We're not going to go through it variable by variable, but we have a section for the cathode, the anode, the electrolyte, the foils, the separator. We have another component that considers other hardware and safety components. And then we have another cost component that estimates costs that change on the size of the manufacturing plant. And this cost change model can be used for any lithium ion cell, but we're going to in particular apply it to energy dense cells of a certain size, of 18650 being the size. And we're focusing on energy dense cells because we want to kind of keep the service that is being provided by the cell as constant as possible. We don't want our results to be skewed, for example, by changes that were implemented to make a lithium ion cell more appropriate for use in an EV or in a power tool. So we're going to look just at energy dense cells, and we're going to control the volume, basically just look at cells, cylindrical cells of an 18650 size, where 18 refers to the diameter and 650 refers to the height. And when we investigate this, we see that the changes in these variables, essentially, they constitute low-level mechanisms of cost change. The overall cell cost in dollars per watt hour changes because these variables change. And so we're going to call changes in these variables low-level mechanisms. Now, of course, this is just a series of variables on a piece of paper or on a slide in this case. We need data to make this real. So we come back to the approach of collecting as much data as possible. This was an extensive effort. We collected data from academic articles, corporate reports, legal filings, specification sheets, industry studies. We have over 1,000 records and over 15,000 qualitative and quantitative data points from over 280 references. I'm showing the data we collected for one of those 41 variables here, the price of the cathode active material. You can see that in general, it's gone down over time. You might also notice that I've highlighted two regions on this plot where the x-axis is time. I've highlighted 1995 to 2000, the late 1990s, and 2010 to 2015, the early 2010s. And that's because due to data limitations, we kind of had to compare a representative technology and look how its cost changed and the various variables changed between these 2 points in time. So we're going to look at cost change between the late 1990s and early 2010s. And for each one of those 41 variables, we developed a representative value, which on this plot I'm showing as these essentially unbroken horizontal lines within each period. And then I've got these broken lines, these dashed lines above and below it to give you a sense of our uncertainty. So we collected all of this data that I'm showing here and much, much more. And then given all of that and given these representative values, we can look at the low-level mechanisms of cost change. I've aggregated some of them here to make it a little bit easier to see what's going on. And we see that the major contributor to cost change for lithium-ion cells between the late 1990s and early 2010s was the increase in cell charge density, the amount of charge you could fit into a given volume. This contributed to just shy of 40% of the cost change observed. The second largest contributor was the decrease in the materials prices for the cathode. The third largest contributor were the costs related to the size of the manufacturing plant. But we also see that many different changes contributed significantly to cost decline over time. The price of the electrolyte solution, the amount of charge capacity that's actually utilized when charging and discharging a cell, the price of the anode material and the separator, they all had significant contributions as well. Now, when I teach students, and show them something like this, I say you should always ask, how certain are you in those very concrete single values you're providing? Well, we also wanted to know how certain we should be, how robust our results are to the uncertainty. So we performed a data informed sensitivity analysis where we kind of looked at extreme cases, those upper and lower bounds on the representative values to get a sense as to how robust our results are to our data uncertainty. We find that cell charge density is still really, in all the cases we examined, the #1 contributor to cost decline, followed by cathode materials prices. But there's more uncertainty as to the effect of plant size and other plant size dependent characteristics. And so this can kind of give us a sense as to why, at a pretty technical level, lithium ion batteries improved. But not everyone who's making decisions that might influence lithium ion battery technology development or the development of other energy storage technologies are going to go into lab and try to figure out how to increase the charge density of a material. There are also high-level mechanisms of cost change, which you might have gotten a hint that I'll be talking about, but I've been referring to low-level mechanisms. And these high-level mechanisms can be things like research and development and learning by doing and economies of scale. And with this bottom-up approach, these mechanistic models, we can assign the different variables to which high-level mechanism likely drove that change that we observed in the variable, in the low-level mechanism. So here we're assigning these mechanisms, these low-level mechanisms, to what drove the change, which could be research and development or economies of scale or learning by doing. And we've included an other category as well for things that can't be easily assigned or might have had nothing to do with these three major high-level mechanisms. We can then sum the contributions within each one of these categories. And we find that research and development was the primary contributor to cost change observed, again, between the late 1990s and early 2010s. We find economies of scale were significant, but were secondary. And we again wanted to make sure that our results were robust to the underlying uncertainty, for example, in different plausible assignments of variables to high-level mechanisms. So we performed a sensitivity analysis. We found that research and development really came out ahead in almost all cases. Economies of scale were secondary in almost all. So our ranking is pretty robust to different plausible assignments. And then we can take this one step further. We can take that research and development contribution and ask, well, what fields of research did it come from? So we can disaggregate that high-level mechanism. And we found that most of that research and development contribution was heavily influenced by chemistry and material science, where we're defining material science broadly to include synthesis and characterization and processing of materials. And so over the course of this work, we have found that there were many different changes to cell components and their prices, and many of them were influenced by research and development, specifically chemistry and material science. And in the course of this, we also found that because many of these components changed and had a significant impact on the cost, that cost change relied on the concurrent improvement in many different cell components. For example, people could be improving cathode materials while others were improving anode materials, and they could still combine them into what looked like a lithium ion cell, essentially. They didn't have to reinvent what a lithium ion cell looked like every time they improved a cathode material or an anode material. And so that allowed all of these changes to kind of happen concurrently. So I said I would leave you hopefully with a few conclusions and some implications for further research or public policy making or financial investments. So the first we touched upon earlier, which is that lithium ion technologies might achieve faster cost decline for stationary applications. An implication of this is that interpretations based on measures of past improvement might benefit from considering important non-cost characteristics. So if you're going to use estimates of past improvement to try to figure out what happens to a technology going forward, it might be useful to look at important non-cost characteristics if they were a major focus, for example, of research and development. Another conclusion was that even after commercialization, cost reduction can be dominated by public and private research and development, while economies of scale remain secondary. So as I mentioned, when first introducing lithium ion batteries, they were commercially introduced in 1991. The analysis I did went from the late 1990s, a couple years later, through the early 2010s. So for a 2-decade period, starting years after commercial introduction, research and development was the primary contributor to cost reduction, which would suggest if you're, for example, going to design a public policy, maybe try to maintain funding for research and development even after commercial introduction. Finally, we found that access to a diverse chemical space might have enabled batteries to improve. So I mentioned how people could try different combinations of first row transition metals like nickel and manganese and cobalt to come up with different cathode materials, for example. This affords you many different options with different ratios, for example, of those three metals. So this is one example of a diverse chemical space. And as I mentioned, those many different cathode options could be combined with different additives in the electrolyte and different anode materials or additives added to the anode materials. All of these different combinations gave just many different ways to make a lithium ion battery, which again did not have to be reinvented. So you could kind of think of the design of a lithium ion battery as being modular and the different chemicals that go into it being drop-in technologies. And while there's more research that should be done to really figure out how much of the modularity might have influenced the price decline or the cost decline of lithium ion technologies, we can say that investments should probably encourage the exploration of diverse chemistries and materials that can be combined in a modular design. This could also help us reduce the chance of suboptimal lock-in. So some have worried that lithium-ion technologies might not be the best technology for every application, but because they're so much less expensive than other options, and people might just keep buying them and installing them, they'll benefit from that additional research and development and production that comes with their increased use. And they will come down in cost so quickly that other technologies can't compete, even if those other technologies might be optimal in the long run. So exploring this diversity of chemical options might also help us reduce the chance of lock-in to a suboptimal technology. I have a number of people I want to thank who helped me with some of this research, notably my advisor at MIT, Professor Jessica Transick, a few other postdocs I've worked with when I study cost trends and cost change, Jong-Yun Sung, Gokshin Kavlak, and James McNerney. The entire Transick lab is listed here, and we have a larger Transick lab pre-pandemic photo. And then I would like to thank the Alfred P. Sloan Foundation, MIT Portugal, and the MIT Office of Sustainability for funding this research. And I would like to thank you for listening, and I'll be happy to take any questions you might have.
Thank you. Thank you for that excellent talk. We have time for questions. We'll start with the students first and then faculty. So if we have students, postdocs, let's hear from you first. All right, then Lynn, you can ask your question.
So thanks for a very interesting talk. So your comment right at the end about modularity triggered a question in my mind. That is that if you think about, I mean, maybe two extremes, a lithium ion battery is a little thing and it doesn't cost very much by itself. A nuclear power plant is a big thing and it costs billions of dollars. And so I'm wondering if as you think across technologies, if it's something that can be divided up into small bits that can be manufactured in a whole bunch of ways, does that have a higher potential for speedy reductions than a nuclear power plant where you only get to build a few planet-wide?
So people have looked into, that's a great question, and people have certainly looked into that. Actually, my advisor, Professor Transick, I think wrote a paper that kind of got at this idea back in, I think, 2006. And I think it might have been the first volume of Environmental Research Letters. There are some hypotheses to that effect. Because I can't really compare it directly to nuclear, I can't say with confidence from my results that, having small things that are produced in a manufacturing line can really, explain the difference in rates. I can say that a few colleagues of mine have looked at why, for example, nuclear power has gone up in price in the United States. And they used a similar cost change methodology, for example, to study the influence of the cost of construction, of the containment, for example. And I would be happy to send over the reference if you're interested. But I mean, this is a general idea that it's possible that something we can mass produce could just come down in price more rapidly. But I think it's an area where we need to do more research to really kind of figure out why these technologies change. A lot of the research historically has kind of looked at trends and then come up with hypotheses based on those trends, but they often infer based on strength of correlation, for example. And the one thing I liked about the approach, the mechanistic modeling that drew me to this research, was that we can kind of figure out why a technology improved. And hopefully we'll be able to come up with a better answer to that question when we can study more technologies.
There's a question in the chat from Jiuzhang. Do you have any comments on the environmental impact of lithium battery disposal?
I do. They, again, it was not something I explicitly addressed in my research, but it is something that is a major concern considering how many of these we're producing. We're taking metals that we're going to great lengths to obtain. At this point, people are trying to get cobalt from the seabed in a serious attempt nowadays, and we're taking all these metals, we combine them, and then we eventually get rid of the electronics. Eventually we're going to have EV batteries that need to be disposed of. There's some great work that's gone into figuring out how to better recycle these materials. But there are concerns that we need to make sure that the appropriate incentives and policies are in place to ensure that these batteries do get recycled.
Inez?
Hey, Micah, I was wondering if you can comment on the recent increase in prices of lithium and whether that was anticipated or no one, meaning the trends that you've shown generally show a decline. So is this like a small glitch in the system as supply and demand equilibrate, or is this a new trend?
That is hard for me to say. That glitch has kind of come out in the last couple months, I believe, is the one that you're referring to. We see, bounciness essentially when you look at how the cost of the technology has changed over time. A couple years ago at this point, people were noticing kind of an almost leveling off in the cost decline of solar photovoltaics, and people were saying, oh, well, we've reached a point where we've hit the materials limit. But in fact, it kind of just turned into a bend, and it came back down to the trend that was being observed for the decades before. I think it's too early to tell whether this is a long-term trend. I do know that many people are looking into mining lithium as well as the other minerals that we need. And for example, a lot of lithium used to be mined in the United States, and then mining shifted to South America, for example, because there was a less expensive approach to mine it. But they could implement some new approaches to bring down the cost in the United States. So I would say it's probably it could very well be some sort of short-term trend, but it would be hard for me to say. It would be premature of me to say whether it's short-term or a long-term fundamental shift.
Inez, please continue.
Oh, if there is a question, yeah, I was going to follow up, but if there is a question from someone else, I would yield it.
Okay. We have somebody in the chat, Shibil. What were the cause of failure or of lithium-ion batteries?
So there are a number of ways lithium-ion batteries can fail, and many of them have built-in safety mechanisms to deal with those possible failures. One example, for example, can be that something can break through the separator. If something breaks through the separator, you get a short circuit. And even the earliest lithium-ion battery cells kind of knew that the designers knew that this was a possibility, and built in safety mechanisms that could render the cell as harmless as possible, given, for example, a short circuit. There are also many different ways that lithium-ion batteries can degrade over time. If you're interested in learning more, feel free to shoot me an email. There's a large literature on studying the different failure mechanisms for lithium-ion cells, both in terms of an extreme event like a short circuit, but also just how they degrade over time and lose capacity.
Ines, you want to follow up?
Yeah, I was just wondering if you could give me a sense of the implications of lithium prices for the overall battery cost then. So I think the trends that are seen right now is kind of a 40% increase in price of lithium. So just in terms of having an order of magnitude, how bad or trivial is this in terms of an added cost to a stationary battery system for grid support?
I would have to double check. So the analysis I did not break it down all the way to the mineral prices. And that's because we didn't have a tremendous amount of information on essentially what a cost equation would be for the production of minerals, or for the production of cathode materials in the late 1990s, right? Because we had to get historical data to make this comparison. I do know that there's been some work that was published by Rebecca Siez, and she one of the conclusions they came to was that they didn't think that lithium prices would completely upend the price of lithium-ion batteries, that they're more expensive components. And in general, people are nowadays often pointing to the first-row transition metals, the cobalt and the nickel in particular, as being the really expensive parts of the cathode. So I don't think, I can already say a 40% increase in lithium is not going to translate to a 40% increase, right? I can already say materials prices are not 100% of the manufacturing cost of a lithium-ion battery. But I would have to double check with some more recent data. The manufacturing of batteries has changed even in the last 5 years, and we didn't have sufficient data to extend our analysis beyond 2015, which is a limitation of our work. But we're hoping that with additional data, we can extend the analysis as the data become available.
Thank you.
A question in the chat from Hannah. Have you looked at battery degradation as it relates to V2G use cases?
I have not. I can point you to a few colleagues who have. It is a concern that we've designed these batteries to hold as much energy as possible, for example, to allow an EV to travel a couple hundred miles on a single charge. And there are one thing to know about lithium-ion technologies is that it's really a constellation of different technologies. And not every cathode material is necessarily appropriate for use in an EV that you want to go 400 miles on a given charge. And some combinations of cathode and anode materials might be more appropriate for a stationary storage application where you're supporting an electric grid. So there is a question as to whether or not essentially all of the effort and energy and materials that went into a lithium-ion cell that's designed for use in an EV, are we really taking advantage of them, or are we maybe wasting them, or if we're using them in a grid application that could be better served by a different combination of cathode and anode that would still constitute a lithium-ion cell. I haven't done that research in particular, but I can definitely point you to a few people who have.
All right. We're almost end of the hour. If there are no more questions, let's thank our speaker once again. Thank you, Micah, for an excellent talk.
I'm sorry, Topdown, can I ask you a question?
Oh, sure. There's a question there. Yeah, go ahead.
So the last or before last slide, you were talking about the progress and the major achievements in R&D were done basically in material science and chemistry. So I was just wondering, so the design itself of the components of the battery or the mechanical design was not really contributed. There were no research that was accumulated that made it more efficient batteries, well, in terms of the design of mechanical parts. And my second question is, if it's a chemical, so would you expect in the recent developments to use of machine learning would help to achieve more in terms of the choosing material in chemical sciences?
So to answer your first question, in terms of this breakdown here, we're not necessarily saying that all of this research and development was exactly the result. We're kind of saying it was heavily influenced by chemistry and material science. And so part of that material science does involve essentially for example, the processing of materials. There are elements to like the design of a battery pack, for example, like if you're going to use pouch cells, you need to design something to keep some pressure on that cell sometimes. That's not being included in this analysis because we're just looking at cell level changes. We're not looking at modules or packs. So any mechanical design that goes into like the heating and cooling of a battery pack are not included in this analysis. So I think if that's what you're referring to, we just limited our analysis to cells. So I don't want to take away credit from all the people who've worked on thermal management, which has been some impressive work. That's just not part of our analysis because we're looking at the cell level. In terms of machine learning going forward, I'm seeing plenty of uses for machine learning, everything from identifying potentially improved cathode materials to figuring out how quickly a given cell might age just based on looking at the first couple cycles of its aging. People are looking to apply machine learning to just a wide variety of components and use cases for lithium-ion technologies. So I definitely think there's potential there to learn more about how we can improve those materials and improve the operation of cells.
All right, thank you. And that concludes our seminar today. Thank you very much.
Thank you for having me.